Hey, here's the Zoom meeting for Physics 231C. This week, we're studying Chapter 6 on rotations. So you need to read the chapter, do the reading quiz. Most people have already done that. And here are some of the equations that you should have written in your notebook while you were reading the chapter. We have an object rotating in space. So it has some shape. There's some axle. It's rotating around an axle. And to describe the orientation of the body, we have an angle. So here's the angle theta. And the rate of change of theta is the angular velocity. So theta is the angular position. The rate of change of theta, or position, is velocity. And we'll call that omega, the Greek letter omega. And the rate of change of omega is the angular acceleration. So it's just like what we had for a particle moving in space. We have a position, a velocity, and an acceleration. Only now these are not position of the center of the object in space. These are the position in terms of the orientation of the body as it rotates. So theta is an angle, omega is an angular velocity, alpha is an angular acceleration. The unit of theta would be radians. The unit of omega would be radians per second. And the unit of alpha would be radians per second squared. So it's very similar to the case of motion in one dimension, which we went over at the very beginning of the semester. Only now the dimension is not the position of the center of the object in some space. It's the orientation, or the angular orientation of the body. Now, some of the concepts that are introduced in the chapter are moment of inertia. So that's denoted I. It's mass times distance squared, where r is the distance from the axis of rotation. So r is the distance from the axle. And delta m is a little part of the body, or a single point, distance r from the axle. Delta mr squared is the contribution of that to the angular, or the moment of inertia, what the textbook calls the rotational inertia, but most books call this moment of inertia, I. And then we sum over all the little parts of the system. So we have the sum of the mass times the distance squared. The kinetic energy is 1/2 I omega squared. So like kinetic energy for motion along a line is 1/2 mv squared. Kinetic energy for rotation around an axle is 1/2 I omega squared. When an object is rolling, then its center is moving and its orientation is changing. So there'll be two kinds of kinetic energy. when an object is rolling. There'll be the familiar kinetic energy of 1/2 mv squared. That's the motion of the center, plus the new thing, 1/2 I omega squared. That's the kinetic energy of the rotating motion. Force is the action that changes acceleration, or actually changes velocity. In Newton's second law, force is proportional to acceleration. Acceleration is rate of change of velocity. Well, for motion along a line, force is the action that produces acceleration. For rotating objects, it's torque is the action that produces change in angular acceleration. So the angular acceleration is r times the acceleration. The torque is r times the force, only it's a little more complicated. It's really r times the force times the sine of the angle between the r vector, the vector from the axle to the position where the force acts, times the force vector, times the sine of the angle between the r vector and the f vector. So this requires some trigonometry and some geometry. So read that carefully and draw a picture of that in your physics notebook. Now, in motion along a line, force is mass times acceleration. Well, it's just the same for rotational motion, only instead of force, we have torque. Instead of mass, we have moment of inertia. And instead of acceleration, we have angular acceleration. So torque is I alpha. All right, so that's the main part about rotation. Now, there are a couple of other sections. There's a section on static equilibrium. A system is in static equilibrium if the sum of all the forces on the system is zero. And that's familiar from Newton's second law. If in static equilibrium, the velocity would be constant, it would be zero. And so the acceleration would be zero. And so the net force would be zero. So this is something we know from before. But there's something else if there are parts of the system that are free to rotate. If there are parts of the system that can rotate, then the sum of the torques must be zero. The net torque has to be zero. And we'll see some examples of static equilibrium, and there's some homework problems on static equilibrium. And then finally, just as in the case of motion in 3 dimensions, we have a related concept of momentum. For rotating motion, we have angular momentum. Now, if you remember, momentum is mass times velocity. Well, similarly, angular momentum is inertia times velocity, only the inertia is the moment of inertia, and the velocity is the angular velocity. So you need to understand all of these concepts and their corresponding equations. You should have them written down in your notebook after reading the chapter. Now let's see how some of these are used in some problems. So here's a problem from the homework problem set 6, which is due on Monday. A solid rubber sphere, say mass m and radius r, is initially at rest at the top of an incline, which has height h and inclination angle theta. it starts at rest and then it rolls down to the bottom. As it's rolling, the center will be moving. That's the velocity v. And the object itself, say a sphere, will be rotating, as in this picture. So in any of these problems, we always start by drawing a picture. So here's a picture of the incline, the ball, the velocity as it rolls down the incline, the angular velocity as it's turning, and now there's a relationship between v and omega. Whenever an object is rolling, the velocity of the center is the radius of the object times the angular velocity. And that object could be a sphere, it could be a cylinder, it could be a hollow cylinder or a solid cylinder. Anything with a geometrical shape, which is spherical, will roll. And the relation between the speed of the center and the angular speed, they're proportional. And the constant of proportionality is just the radius of the object. And that's just really because of the definition of angles. You know, delta x would be the radius times delta theta, where delta theta is the angle defined in radians. By definition, delta theta is delta x over r. The ratio of the linear dimension to the radius is the angular dimension. So delta x per unit time is v, and delta theta per unit time is omega. So this will be an equation important whenever you have rolling motion. Now, what's the question? Well, the first question is, what's the final speed? So we want to know the final speed. And the second question is, what's the kinetic energy? Total kinetic energy, both translational kinetic energy from V and rotational kinetic energy from omega. So first we draw a picture, then we write down the necessary equations. Kinetic energy is a half mv squared plus a half I omega squared. Now what's I? I is the moment of inertia. The moment of inertia of a solid sphere is 2 divided by 5 mr squared. There's a table in the chapter which gives moment of inertia for various kinds of circular objects. And of course, speed is r omega, this equation. So if you combine these two lines, you see the kinetic energy of the rolling sphere is not 1/2 mv squared, the kinetic energy we've dealt with before. That would be true if the sphere were an ice cube, just sliding at a velocity v. But if it's rolling, it has another contribution to kinetic energy, which is 1/2 I omega squared. So in fact, the kinetic energy is 7 divided by 10 mv squared. Now we're going to solve this problem using conservation of energy. So we can say 7 over 10 mv squared plus mgy is constant. 7 over 10 mv squared is the total kinetic energy. Mgy is the total potential energy, just the gravitational potential energy, where it has a height y. And that's a constant. So we have various equations here. One thing what they want to calculate is the speed at the bottom, v final. Now we can get that from the kinetic energy at the bottom using conservation of energy. At the bottom, the kinetic energy is 7 over 10 mv final squared. And at the top, the total energy is mgh. And these are equal by conservation of energy. So this quantity is constant. At the bottom, y is 0, and it's just 7 over 10 mv squared at the bottom. At the top, v is 0, because it starts from rest at the top, and y is h. So the energy is mgh at the top, it's 7/10 mv final squared at the bottom, and those have to be the same. So we can immediately solve for v final. The m's cancel, multiply through by 10 over 7, and take the square root. And that's the first question. The second question is, what's the kinetic energy at the bottom? Well, we could say it's 7 over 10, 7 over 10 m v squared, where v is the velocity at the bottom. Or we could just say, well, it's the same as mgh, because the kinetic energy, all of the energy at the bottom is in the form of kinetic energy, and all the energy at the top is in the form of potential energy, mgh, and they have to be the same. So there are the two answers. Here's another problem from the assignment. This is the assignment, which is due Monday. A string is wrapped around a pulley, and a weight hangs from the other end of the string. So let's start drawing our picture. Well, we have a pulley, so it's a disc. We have a rope around the pulley and attached to a weight. Now we allow them to, we might start with some height of the weight, and then we have everything at rest. But now we let go, the weight will fall down, the pulley will turn around. We assume that the rope is attached at some point on the pulley. So as the weight goes down, the pulley goes around. One question is, what's the angular acceleration of the pulley? The other question is, what's the angular velocity when the weight hits the floor? So we draw a picture, there's the picture, and we label it. We don't label it with the numbers given in the problem, we label it with the symbols, like the radius of the pulley, is this R. The mass or the weight of the weight is mg. It doesn't tell you what is the mass of the pulley. So the mass of the pulley is not given. It does tell you what the mass of the weight is. Oops, I've lost my picture. Let's see if I can get the picture back again. Hold on a second. All right, I'm not getting the picture, so let me try again here. All right. So let's think about some of the equations. Well, we do have a torque here. So we could say moment of inertia times alpha is the torque times R times the tension in this rope. Remember, torque is distance times force. Distance here is R, the radius of the pulley that forces the torque exerted by the rope. I don't think we actually need that. All we really need is the relation between alpha and the acceleration of the weight, because what's given here let's see. What's given is the acceleration. That's 3.3 meters per second squared. The radius, that's 2.4 centimeters. And the height that the weight drops from. So, just as the angle is the radius, the angle is the distance divided by the radius. That's the angle in radians. Angular velocity is the rate of change of the angle. So that's the angular velocity divided by the radius. The angular acceleration is the radius, no, the velocity divided by the radius. Sorry, angular acceleration is acceleration over radius. Well, the acceleration is given. So in fact, for the first question, what's alpha? All I have to do is put in the value of A, which is up here, and divide by the radius of the pulley, which is up here. And that's the answer. I mean, the answer is going to be, as usual, a unit and a number. The unit will be the unit of alpha will be meters per second squared. That's A divided by meters. So it'll be 1 over second squared, or since alpha is an angular measure, it'll actually be radians divided by second squared. So I'll get some number of radians per second squared. I guess I've crossed this out here. Solve for alpha. It's something like 130 radians per second squared. Do this calculation accurately with a calculator. Now, as for the speed where the weight hits the floor, well, we have here a case of constant acceleration. Alpha is a constant. It's not constant motional or translational acceleration. It's constant angular acceleration. Well, you remember the equations for constant acceleration. In the case of motion along a line, delta V is 2a delta x. Well, I can convert that into rotational motion as long as I have constant acceleration. Delta omega squared is 2 alpha delta theta. Alpha I already know because that was the first question. And what's delta theta? Well, if the mass here goes down by a distance h, then the wheel will turn by an angle h divided by r by in radians. So by the radian measure of angle, delta theta is h over r. Now, I'm supposed to calculate omega at the floor, so I have to take the square root of this. Omega starts at 0, and then it increases up to some value omega, which will be just the square root of delta omega squared, square root of 2 alpha h over r. Here's another problem. This one involves a torque. In fact, this is a problem with static equilibrium. So, we have a ladder leaning against a wall in static equilibrium. There's friction at the base. That prevents the ladder from falling down. If there were no friction here, the ladder would just slide down the wall and fall down. So you have to have a frictional force here, or else you have to block the ladder on this side from sliding out from under you. But anyway, we'll assume that's just friction with the ground. Now, there could be friction with the wall, but we'll neglect that to make it simple. So the ladder is not going to slide down because of the friction here. We'll neglect friction at the wall. Now we want to know what's the force of friction at point B. And some information is given, the mass of the ladder and the length of the ladder. So what we're supposed to calculate is force of friction. Now, step one is to draw a picture. So here's the picture. Here's the wall, here's the ground, here's the ladder. Okay, that's a start. Let's put on this picture all the forces that are acting on the ladder. So gravity is pulling it down towards the earth. We can assume that force, or we can calculate that force by saying that it's all concentrated at the center. It's the total force of the it's the total gravitational force, Fg. And I can think of it as being all concentrated at the center. So Fg is the gravitational force. It's equal to the weight of the ladder, mg. And as for its location, strictly speaking, it's located at all points along the ladder. But I can approximate that, or I can express that as if all the weight were just concentrated at the center of the ladder. That'll give me the total force. Now, there's a contact force with the wall, but no friction. So that's just a normal force. There's a normal force at the ground. So let's call that Fn. And then there's a frictional force, which is opposite to the direction that the ladder would slide if it could slide. If the ladder could slide, it would slide out to the left. So the frictional force is to the right. So I have these four forces. For static equilibrium, the sum of the forces is equal to 0. Now, these are all vectors. So I can, first of all, take the horizontal vectors. F sub f to the right plus f sub c to the left must be 0. So f sub f minus f sub c is 0, where f sub c points in the other direction. So that's where the minus sign. Now, as for the vertical forces, I have Fn up and Fg down. So I have F sub n minus F sub g is 0. The net force is 0. So there are the net forces in the two directions. Those are 0. And now I need one more equation, which is that the torque around any point on the ladder is 0. Now, I could calculate the torque around this point, or I could calculate the torque around this point, or I could calculate the torque around this point. But it'll be easiest if I calculate the torque around this point. Call this point B something. Call this point B. Remember, torque is force times distance. Well, for this force, the distance is 0. That's the distance to the axle. I'm thinking of this as rotating around the point B, so that distance is 0. Similarly, F sub F, the torque is 0 because the distance to that point B is 0. So there'll be two torques. There's the torque due to the force of gravity, and there's the torque due to the force exerted by the wall. Now, those are torques in different directions because this force will cause a rotation around this way, but this force will cause a rotation around the other way. So there'll be a positive torque and a negative torque. Torque is distance times force. In the one case, the force is Fc and the distance is L, the length of the ladder. In the other case, the force is mg, gravitational force, and the distance is L over 2, because that's the distance from the base B to the center, where I'm saying all of the gravitational force is just located at the center. But then there's the sine of the angle. And that's what makes this problem a little difficult. So torque is RF sine phi, let's call it, RF sine phi, where phi is the angle between the R vector, the position vector, and the force vector. Now this angle here is 180 degrees minus phi, and the sine of 180 minus phi is the same as sine of phi. And by looking at this little right triangle, the sine of this angle, the opposite to the angle is the perpendicular distance, the distance from the axle to the force of the line of the force. We call it R perp. So calculating torque is a little tricky because of the trigonometry involved. But anyway, I'll have this equation. Fc times L times the sine of theta. What's theta in this case? Theta in this case is 75 degrees. This theta. This is the sine. So that's Fc L and then sine theta, and then minus, because it's in the other direction, Fg L over 2, only a distance L over 2 from B. And in this case, the angle is actually the sine of, the angle here is 90 degrees minus theta. So the sine of that is the cosine of theta. All right, so these are the equations for equilibrium. I have here 3 equations. There are 3 unknowns. The 3 unknowns are force of friction, the normal forces, everything else is given. So what am I supposed to calculate? I'm supposed to calculate the frictional force. So FF, FC, and FN are the 3 unknowns. You have to solve these 3 equations simultaneously. So it's algebra, but it's an algebra you're familiar with. Multiple equations, you sign for multiple unknowns. And the final answer will be one of those unknowns, namely the force of friction. Force of gravity is not unknown. It's just the weight of the ladder. This next problem has to do with the Bohr model of the hydrogen atom, an old theory of the hydrogen atom going back to the early part of the 20th century, where the theory is there's an electron revolving around on a circular orbit around the proton at some radius r. And the question is, what's the angular momentum? Now, r is given. and the speed is given. So the speed is given, the radius is given. What's the angular momentum? Well, I have to know the definition of angular momentum. So if you go back and look in the chapter, MVR, or you should have written this down in your notebook. M is the mass of the electron. You can look that up anywhere. You can look that up on Google. Just Google, what is the mass of an electron? Get the answer in kilograms. And then the other part of this problem is to compare this to a fundamental constant of nature called Planck's constant. And in fact, this quantity will be equal to Planck's constant divided by 2 pi. If the polar ice caps melt, there'll be more liquid water in the oceans. That will increase the moment of inertia of the Earth, and it's estimated by 0.3%. What effect will that have on the length of a day? And the way to solve this problem, why would increasing the moment of inertia affect the length of a day? Think about it. Angular momentum is constant unless something outside of the system exerts a torque on the system. But if there's no torque on the system, then angular momentum is constant. It's just like momentum is constant if there's no external force. Well, in this case, angular momentum is constant if there's no external torque. Now, angular momentum is I omega. So if you change I, you must change omega by a compensating factor so that I times omega is constant. The angular momentum is constant. The moment of inertia is not constant. Omega has to be not constant so that the moment of inertia times omega will be constant. So we always draw a picture. Here's a picture of the Earth with its ice caps, a northern ice cap and a southern ice cap. Suppose the ice melts, all of that water, which is in the cold regions of the Earth, in the North Pole and the South Pole, will melt and flow, because liquid water is fluid. It'll flow around to the outside of the Earth, and you'll have that water distribute around the outside of the Earth. You see, that moves this mass, which is close to the axis of rotation, far from the axis of rotation. So that increases the moment of inertia. Remember, moment of inertia is mass times distance squared. Well, the distance has increased as this ice moves from r equals 0 out here to r on the surface of the Earth. So here's the conservation law. I1 omega 1 is I2 omega 2. Now, omega 1 is 2 pi over 1 day. It's the angular velocity, so it's the distance, 2 pi, over the time, 1 day. It takes 1 day for a point on the Earth to go around the axis. So omega 1 is 2 pi over 1 day. That goes with moment of inertia I1. But now the moment of inertia is going to increase to I2. So now calculate omega 2. So omega 2 will be omega 1 divided by the increase in moment of inertia, 1.003. 3 parts of 1,000, or 0.3 parts of 100. 0.3%. 0.3%, it says. So there you can calculate omega 2. The time is T2, is 2 pi over omega 2. It'll no longer be a day. It'll be a little longer than a day. So the Earth will slow down. It's just like the problem of the ice skater who's spinning around. When she's spinning around with her arms pulled in, she goes at a certain speed. When she pushes her arms out to the outside, her moment of inertia increases, her speed slows down, And so the period of rotation will be longer. So what it asks is, what's the effect on the length of a day? Well, the time will increase by some number of minutes. All right, so we're finishing chapter 8 on rotations. That homework assignment is due Monday. The next midterm exam will be Tuesday. So midterm exam number 2 is coming up Tuesday, March 12th. And it will consist of 4 parts, chapters 5, 6, 7, 8, on energy, momentum, oscillations, and rotations. Remember, for the exam, you need to have an equation sheet of equations or pictures, diagrams, whatever, things you can refer to during the exam, so you don't have to memorize all the equations. So before Tuesday, March 12th, you should have an equation sheet, handwritten, 1 page, 2-sided, of the important equations from these 4 chapters, which you'll use during the exam. The exam will be like the first midterm exam, 70 minutes long, and between 7 p.m. and 10 p.m. at Tuesday night on Lon Kappa. So read the instructions and information about the exam on Lon Kappa. There's a Lon Kappa page where you can read about the exam. Look at the practice exam to see what kind of problems might appear on the exam, and make sure you have your exam sheet ready.